Winnie, when you're ready, feel free to start. Thank you.
Okay, thank you. So hi everyone, I'm Winnie Chen from the University of Hong Kong. Today I'm going to share with you my study on children's knowledge of math vocabularies. Language and math are related because language helps people to refine their math concepts. Math vocab is a kind of language skills. They are actually words that are specifically related to mathematical contexts. There are two types of math vocabs in early mathematical learning, quantitative and spatial. Previous studies have shown that math vocab is a predictor of children's math performance. And in our previous study among elementary school students, we have also found that math vocab is an important mediator in predicting children's word problem performance. Math vocab is a kind of language skills, and at the same time, it is related to many early numeracy skills as well. For example, verbal counting, number comparison, etc. So this makes us ask the question of whether math language is simply the adding up of general language skills and numeracy skills, or math language is more than that. This question will help us to decide what children actually need to acquire in their early childhood. Related to that issue, we have set up two research questions. The first question, we want to know if math vocab is still an important predictor of early math performance after taking into account both general language skills and numeracy skills. The second question is, we want to look at the relation between math vocab and different domains of math performance. We invited 102 Chinese-speaking kindergarteners in Hong Kong to take part in our study. It was a longitudinal study with two phases separated by one semester. The children completed a series of cognitive skills tasks, including a listening comprehension test, which was used as a proxy of general language skills. They also completed tests on numeracy as well as math vocab. In the second phase, we assessed children's performance in 4 different domains in math, namely applied problem solving, quantitative concepts, math fluency, as well as calculation. In our regression model, we found that math vocab remained as a significant predictor of applied problem solving after entering the other cognitive predictors. And it was also a significant predictor of quantitative concepts. However, it was no longer a significant predictor of math fluency as well as calculation. In our data, we show that math vocab is still a unique predictor of both applied problem solving and quantitative concepts after taking into account language skills and numeracy skills. So it seems that math vocab is more than simply adding up language skills and numeracy skills. There may be some special elements in math vocab beyond language skills and numeracy skills that makes it a unique predictor of children's math performance. This highlights the importance of acquiring math-specific vocabularies in early childhood. In our data, math vocab is not a significant predictor of math fluency as well as calculation. So probably math vocab plays a more important role in understanding and applying numerical concepts rather than in performing arithmetic. Here are the references. Thank you for listening. You're welcome to ask any questions, or if you like, you can send me your comments through email. Thank you.
Thank you, Winnie. We have time for a few questions. I'm just waiting to see if anybody wants to ask me. Elisabeth, maybe you can start setting up.
Yeah, sure. Thank you. Okay, so can everyone see my screen?
I can't.
You can't?
No.
Oh, interesting.
Okay, now we can
Okay.
see it.
Dude. Can you still see it now?
Yes.
Okay, awesome. Great. Let me just minimize the windows. Okay, so hi everyone, I'm Elisabeth. I'm a PhD student at UCSD working with David Barner. And the topic of my talk today is, do bilingual children subitize differently across languages? So the broad question that we're interested in is, how do bilingual children acquire counting across the two languages? Oops. All right. So the first and most direct investigation of small number words acquisition in bilinguals was conducted by Wagner and collaborators. So in this paper, French and Spanish English bilingual children were tested on given number task in their two languages. So given number task is a task in which children are provided with a set of counters and they are asked to give specific number of counters. And so using that task, previous studies of monolingual kids have shown that the process of number words acquisition in monolingual children is progressive. So follow this progressive order, such that first children become one knower. So these kids are able to reliably provide one object under request, but they can't give consistent responses for larger requests. Then children become two knowers, so they can reliably give 1 and 2, but not reliable responses for larger numbers. And so following a similar pattern, they become 3 knowers and 4 knowers. And after going through these subset knower level stages, they then seem to understand how counting works. And these kids are often called CP knowers or cardinal principle knowers. All right, so what about bilingual kids? So Wagner and collaborators found that the knowledge of small number words, so numbers from 1 to 4, didn't really transfer across languages, such that bilinguals had tended to have different knower levels in their first and second languages when they were subset knowers. However, bilingual children who were classified as CP knowers, so kids who understand how counting works in their L1, tended to be CP knowers as well in their L2. And so those results suggest two main characteristics of bilingual number words acquisition. So first, it suggests that bilingual children initially need language-specific training on small number words in order to develop this exact meaning for those small number words in both languages. And second, in respect to CP knowers, it raises the possibility that bilingual kids who advance quickly through the knower level stages in their L1, so becoming CP knowers, might become CP knowers in their L2, despite not having passed through the same subset stages as they did in their L1. So basically, by virtue of a transfer of procedural counting knowledge across the two languages. And so in this project, that's the question that we wanted to investigate here. And so specifically what we did is looking at subitizing ability of bilingual children across their two languages. And here what I mean by subitizing is, so I'm referring to this ability to quickly and accurately map number words to small sets, so usually 1 to 4 dots without counting. So our specific goal was to test whether children who are CP knowers in both languages also master the meaning of small number words in both languages. All right, so to do this, we tested 66 Spanish and German English bilingual children, all aged between 2 and 5. And kids were presented with 3 tasks. So given number of tasks that I described earlier, that was to make sure that they were CP knowers in both of their languages, and also a subitizing task. So this is a task in which children are presented with flashed arrays of dots, and they need to guess how many dots they see on the screen, and also a counting task. So just asking them to count a set of objects. And importantly, they had to perform those 3 tasks in both languages. All right, so here are the results. So in the y-axis, you have children's subitizing accuracy, and in the x-axis, you have numerosity, so the number of dots that represented the kids, and the different columns represent kids' performance across the 2 languages. And here, NL1 refers to the number language, so the language in which they were more comfortable counting. And so what we found overall is that kids were pretty accurate at subitizing quantities 1, 2, 3, and you see kind of starting to have a decline starting at the numerosity 4. However, what's important with this finding is that we found a consistent difference in subitizing accuracy of bilingual CP-knowers across languages. So in particular, we found that these bilingual kids subitize more accurately in their first number language relative to their second number language, and that is despite being CP-knowers in both languages. All right, so again, so the conclusion here, so we found that bilingual children who are classified as CP-knowers in both languages still show differences in subitizing. And so this suggests that bilingual children might learn to apply a counting procedure in their second language independently of learning meaning for small number words. And this is interesting because it kind of opens up, in theory, this possibility that this process could also occur in monolingual kids, so that it would be possible for kids to become a CP-knower despite not having passed through all the subset knower level stages. So this basically, the CP rule and the acquisition of small set could be a learning process that occur in parallel. All right, so we're still in the process of analyzing our data, and future direction include, so we want to see how counting experience relate to differences in subitizing in these bilingual kids, and we want to see how bilingual subitizing ability compared to monolingual subitizing abilities. All right, and so I would like to thank all the listeners and my lab and our funding agency. Thank you.
Thank you. I will open for questions.
I have a quick question.
Yeah.
That was super interesting, so thank you. I'm just curious if, on average, do bilingual children transition to CP-knower status later than monolingual children?
Yeah, that's a good question. From our data, we see that there tends to be a little delay. Yeah, so we tend to see that. Yeah, it might also depend perhaps on our population, but here we didn't see any difference between our German kids and our Spanish kids.
Okay,
Yeah.
Cool, thank you.
Yeah, thank you.
Thank you. And so Nicholas will go next. Sorry, I think Marta had a question, so please go ahead.
Yeah, I can hear you.
I'm happy to ask it, but I'm also happy to let Nick go ahead. But I mean, my question had to do with the nature of the errors when they don't subitize correctly. Did it seem like they were just getting the wrong word, like they were really doing it, but just selecting the wrong word because they're less comfortable in that language? Or were the errors just off by 1 usually, so they were kind of in the ballpark? I was just curious.
That's a great question. We haven't had time to look at specifically the type of errors that they're making, but from what I've seen so far, it's not going to be off too much. It's still like it seems that they're trying to have the correct number, but they just don't quite know oftentimes, like they don't have the association basically between the labels and the quantities.
Okay, thank you.
Thank you.
Thank you. Nicholas.
Okay, I can go ahead. All right, hi everyone. So I'm Nick Vest. The title of my talk today is How do children's concepts of zero relate to their understanding of integers? So imagine asking yourself the question, what is zero? It's kind of tricky to think about, but this question could be even more difficult for children. Indeed, research suggests that children have vague concepts about zero. And so what are some of the concepts that children might hold? Children might start with the concept of zero as nothing, which we coin the null concept. And through time, however, they may shift to a more sophisticated concept of zero. That is, children may begin to understand zero as the symmetry point between positive and negative integers. If this is the case, as children advance in their understanding of zero, they may actually shift in their thinking about integers as well. So what are integers? An integer is a number with no decimal or fractional part that includes positives, 0, and negatives. People represent these numbers on a mental number line with positives to the right, negatives to the left, and 0 in the middle. In the current study, we addressed two questions. First, what are children's concepts of zero? And second, are children's concepts of zero related to their understanding of integers? Now I'll explain how I answered these questions. I collected data online from 80 children in 4th through 7th grade. And the findings I present today will reflect only a subset of the data we collected during these sessions. First, I asked children two questions. The first question is, what is zero? And the second question is zero a number, why or why not? Then I asked students to solve 4 additive inverse problems. So the additive inverse principle states that any integer plus its inverse equals 0. And you can use this principle to solve the problem. If you do it this way, you might actually solve the problem faster than if you were to compute it from left to right. And so we collected the time it took for children to solve each problem. And then after children solved the problem, we also asked them to explain the steps that they took to solve the problem. Next, we had children choose where they think the number 3 would go on the number line. So we use this as another measure of children's integer knowledge. So for example, if a child chose the letter A, we might think they have a null concept of 0 and presume 0 at the beginning of the number line. But if a child chose letter B, we might think they have a symmetry concept and presume 0 is in the middle of the number line between positive and negatives. Last, children were given 2 minutes to solve 26 integer addition problems. This was to test children's fluency with operations involving integers. Now I'm going to dive into the results. So all the children expressed a null concept of 0. Some also expressed a symmetry concept of 0. And so we categorized children into 2 groups, those who provided a null concept only, and those who provided both symmetry and null concepts. And so on this plot, we have 0 concepts on the x-axis and count on the y-axis. A majority of the children in the study generated a null-only concept of 0. When we split this by grade, 4th and 5th graders provided more null concepts, while 6th and 7th graders provided more of both the symmetry and null concepts. And this finding was statistically significant. Recall that we coded explanations for use of the additive inverse principle. In this plot, we have 0 concepts on the x-axis and probability for using the additive inverse principle on the y-axis. While it appears those with the symmetry and null concept were more likely to use the additive inverse principle, the relation here did not reach statistical significance. We also coded reaction times for using the additive inverse principle. And so in this plot, children who held the symmetry concept of 0 were more likely to use the additive inverse shortcut as indicated by reaction time, and this finding did reach statistical significance. In the number line task, children were placing 3 on the number line. And so on this proportion plot, we have 0 concepts on the x-axis and proportion for each choice on the y-axis. Children with the null-only concept chose A more than those with the symmetry and null concepts. However, in a model, this difference did not reach statistical significance. Last, we examined whether concepts of 0 related to symbolic fluency. So children with the symmetry and null concept of 0 solved more problems correctly than those with the null-only concept of 0. And this was statistically significant. In sum, 4th through 7th graders generated different proportions of null and symmetry concepts of 0. These concepts did not predict explanations about the additive inverse principle. However, they did predict use of the additive inverse according to reaction time. Concepts did not predict choices on a number line. However, concepts of 0 did predict symbolic fluency. While our results suggest mixed evidence, these data all showed patterns in the anticipated direction that a symmetry concept of 0 may relate to a broader understanding of integers. If this holds true, we can inform teachers about best practices for talking about 0 integers in the classroom. Thank you to my advisor, Marta Alibali, my lab mates, and the RAs that have helped me with this project. And thank you all for listening to my talk today.
Thank you, Nicholas. We have time for maybe one question.
I have a quick question.
Mm-hmm.
So when you examine the relation between like the serial understanding and, for example, arithmetic fluency, have you controlled for grade? Because there's a significant grade difference in the understanding of serial.
Yes, that's a great question. So I would have to do that, and I honestly I would imagine that perhaps that would maybe that would capture some of the variance that we see in that, and so yeah, it's possible that that would explain some of the differences there. Thank you.
Thank you. Terry, when you're ready.
Okay. Let's. You see my screen? Okay, so today I'm going to talk about a new study which I assess students' ability to identify unknown in word problem solving. So we investigate word problem solving because a lot of students have difficulties in solving word problems. And to look at the difficulties, we need to first understand the word problem solving process. So this is one of the models that explain the word problem solving process, and there are 5 stages. The first stage is text comprehension. Basically, students need to understand the text, and then they form a representation of the problem scenario in their mind in the situation stage. And then in the third stage, the mathematization stage, the problem solver actually convert the problem scenario into a numerical expression, like a number sentence. And then they do the calculation and interpret the answers. So we hypothesized that the difficulties in solving word problems lie in the mathematization stage, but unfortunately, we don't know much about this stage. So based on the literature, we propose that there are at least 2 important steps in this stage. The first one is schema identification, and the other one is unknown identification. So let's take this word problem as an example. You can put 5 apples in the box. Now there are 2 apples in the box already. How many more apples can you put into the box? The first thing we need to do is we need to understand that this is a combined problem, so that the general formula would be something like this: part 1 plus part 2 equals total. So this is schema identification. But the process doesn't stop here, because we still need to put the numbers into the right positions in the number sentence. So here we know that the total is 5, and one of the part is 2, and we are asking for the other parts. So if we are able to put numbers in the right position, then we should be able to get the answer. So in this study, we developed a novel measure that assesses whether children are able to identify the position of unknowns. So we create 6 conceptual diagrams about multiplication and division. So 3 of the diagrams represent multiplication and 3 of them represent division. So besides that, we also vary the unknown position in these diagrams. So here is the unit size unknown condition. This is the number of unit unknown condition, and this is the total unknown condition. So what students have to do is we give them word problems like this, and they have to match the word problem to one of these conceptual diagrams. So here, this one is a division problem, and the unknown position is the unit size. So this is the correct answer. So the question we are asking is whether 5th graders can identify the position of unknown from these word problems. And if they can, does this ability predict future math problem solving, and why? So we have more than 200 4th graders being assessed 4 times on these measures. And let's talk about the scoring of this task first. There are 2 ways of scoring. The first is a stringent one, in which the student have to be correct in terms of both the operation involved as well as their unknown position. The second scoring rule is that they get a mark as long as they get the unknown position correct. The process or the operation doesn't matter. So the data suggests that using scoring rule 2, the reliability is actually higher, and the results remains the same pattern of results is obtained. So we will use scoring rule 2. So these are the correlation and the descriptive statistics. As you can see, out of a total of 12, the mean score of participant is just 6.6, which is far from perfect. And we also see that these abilities significantly correlate with math problem solving performance. So we move one step further to test whether these unknown identification skills actually predict future math problem solving after controlling for IQ and working memory and autoregressive math problem solving. And after controlling for all these unknown identifications still predict future math problem solving. And we move again one step forward to identify the potential mechanisms. And we found that unknown identification actually predict future math problem solving through number sentence writing, but not computation. So this is the summary. We find that fifth graders have the ability to identify unknown positions from multiplication and division word problems, but their performance was far from perfect. And this ability actually predict math problem solving 1 year later after controlling for IQ, working memory, and autoregressor. And this relation was explained by the ability to write number sentence, but not computation. So we believe that this study provides a strong rationale for us to incorporate schema instruction into our math curriculum, because schema instruction actually teach students to identify problem schema as well as putting numbers into the right position in the formula. So, and as you can see here, when students do not receive schema instruction or other kind of instruction that teach this kind of thing, so their performance was far from perfect, and there's a large room for improvement. So that's all for my presentation, and I would like to thank this party as they enable this study to be conducted. So this is the Q&A section. So if you have any questions, feel free to let me know, and you may also direct your question to me through email.
Okay, I think maybe Allison can start.
Sure. Give me 1 second to pull my slides. Okay, is everyone viewing the slides? I can't even see if you guys are responding, so I'm gonna assume that we're good.
Yeah, we can see that.
Okay, perfect. So hi everybody, my name is Alison Vrabec. And I completed this project actually for my master's thesis at the University of Dayton, along with Dr. Mary Foos. And my topic was exploring the effects of an adaptive number ebook on parental attitudes towards mathematics. So a little bit of background information. We understand that math is a strong predictor of children's later academic achievement. But we also see many trends where parents are engaging in home literacy activities more often than they are engaging in math activities. So I decided to look into some reasons why this may be happening and found some literature to suggest that it is not parental attitudes towards mathematics. So believing that math is important, that young children should learn math and understand the practical applications of learning math at a young age, but it's actually this level of parental uncertainty where parents feel that they are unable to either teach their children math effectively or are uncertain of what actual math activities are appropriate for their children at the specific age. And this is likely what prevents them from engaging in math activities at home rather than just in general having negative attitudes about mathematics. So for my project, I decided to examine a possible way of improving this parental uncertainty and these parental attitudes. I did this by using a novel ebook, which was developed by Dr. Foos and some of the University of Dayton's computer science department. So the ebook used non-symbolic numerical comparison. So it was essentially like a traditional storybook. It presented children with the idea of going to the zoo and counting the animals in the exhibits. And the ebook would have 2 pages, and each page would ask children to determine which one has more of whatever animal was on the screen. It had an adaptive version and a non-adaptive version, in that the adaptive version would advance to a harder level if the child was getting many of the questions correct, and would maintain them at a level if they were struggling or getting questions wrong until their scores improved, while the non-adaptive version just maintained them at the same level regardless of their performance. So the goal of this adaptive version was that this would eliminate some of that parental uncertainty because it would automatically advance the children to a more difficult level when they were ready, and the parents were not the ones having to make that decision. And we hope that this would thereby improve their attitudes towards mathematics. So in terms of my specific hypotheses, I predicted that parents would rate their children's math skills as being improved more after reading one of the experimental ebooks as compared to a control ebook, which was just a traditional literacy ebook about a story and had no math components. And I predicted this effect would be strongest for parents who received the adaptive version of the ebook. I also predicted that parental attitudes towards mathematics at post-test would be more improved after using one of the experimental ebooks as compared to the control group. And this again would be strongest for parents who had the adaptive version. For the measures used in my study, I collected baseline demographic information. I used the early math questionnaire, or the EMQ, to measure parental attitudes towards mathematics. And then I had originally intended to assess children's math skills directly, but due to the pandemic, which was, I started collecting data collection in the middle of the COVID-19 pandemic, I had to switch to a measure that could be done remotely. So I instead used this parent assessment of children's math skills, which relied on parental ratings of their children's skills rather than direct assessment of the children's skills. So asked parents to rate children's abilities to, I believe the questions were, can your child calculate simple sums such as 1 + 1, 2 + 2? Which integers 1 through 15 could their child identify, and how high could their children count? To supplement this measure, I added a few questions of my own that mimicked the specific skills that were seen in the ebook with this numerical comparison. So I included pictures of apples in baskets and asked parents if they believed that their child could identify which basket had more. So very similar to what they did in the ebook. I ended up with a total of 65 participants. The average child was about 4 years old, male and white. The average parent was a female who identified as the child's mother and had a bachelor's degree as their highest level of education. So in terms of my results, I ended up with a much smaller sample size than I wanted due to difficulties with remote data collection during the pandemic. So this did limit some of my statistical analyses. So when looking at parental attitudes towards mathematics, so those early math questionnaire scores from pre to post test, I found no significant main effect. So I decided to look at effect sizes and found a small effect size for the adaptive condition when compared to the other two conditions. And the direction of this effect indicates that this may have been related to improvements in parental attitudes towards mathematics. This may possibly be due to the adaptive nature of the ebook, but again, due to the small sample size and the low statistical power, it's hard to determine that for sure. Parent rating of children's global math skills, so that the overall measure, looking at how high children can count and things like that, had no significant main effects and no significant effect sizes to note. But parent ratings of children's specific math skills, so the supplemental measure that I added, did have a significant main effect as well as some effect sizes to note, where the adaptive condition was associated with the direction of the effect associated with higher parental perceptions of children's specific math skills when compared to the other two conditions. And again, this may be because the parents were able to see their children perform a very similar task to what they did in the ebook. They may have in turn rated these skills as improved. However, again, it's hard to determine because this was only based on parent perception of their children's skills and not a direct assessment of their children's skills. And again, this was underpowered due to some limitations from COVID-19. So some future directions would be to continue testing our ebook and see what kind of impacts it can have on children's math learning, and also to again examine these children's math skills in a direct way rather than using parental perceptions. And again, just get a larger sample size and see if we can really flesh out these trends in parental attitudes towards mathematics and parental uncertainty. And that is all I have for you guys. So I'm gonna stop sharing so I can actually see everybody. And then if there are any questions, I'm happy to answer them. Okay. Thanks, everybody.
Jake will go next.
Is that working?
Yes.
Awesome. All right, so yeah, hi everyone. My name is Jake. I'm a PhD student at Vanderbilt, and yeah, I'm going to talk a little bit about some work I was involved in my first couple years here. So, so we know that early symbolic number skills predict growth and performance on later math measures in the first few years of formal schooling. And pre-kindergarten symbolic number skills are single best predictor of later school achievement. And although the importance that these symbolic number skills play in our lives is clear, we're still cultivating an understanding of how to develop a strong symbolic number system. And one important domain that could impact symbolic number development is language. So language skills have been found to have a direct and unique relation to early numeracy skills, with different language skills appearing to relate to different components of symbolic number skill. So for example, phonological skill, which is our ability to recognize and manipulate sounds, appears to be related to symbolic skills that don't involve a quantitative understanding. So skills like reciting the count sequence, verbal counting, whereas semantic knowledge, which is our understanding of what words mean and represent, appear to be related to symbolic skills that involve a quantitative understanding. So that could be skills that involve mapping to numerals. So for example, number comparisons. So with that in mind, previous research has mainly used phonological skill or semantic knowledge as a proxy for language skill in general, making it difficult to accurately assess how these two language skills may be related to two different components of symbolic number skill. And furthermore, although we know that there are these relationships, it's still a little unclear of what the mechanisms underlying these relationships are. So we went out to examine how both phonological skill and semantic knowledge differentially relate to symbolic number skills, specifically Arabic number comparison, because being able to identify the larger of two numbers is often how we judge if an individual understands what numbers are. And second, we wanted to examine the mechanisms underlying these relationships. So for semantic knowledge, we proposed a symbol mapping mechanism to be underlying the relationship, where for words or images, you have to map from what the symbol is to what it is representing, what it means. For example, here, you have to understand that I use a fork to eat and I use a spoon to eat. And then for semantic knowledge, we often make a related judgment. So are these items related? Similarly, for numerals in a number comparison, we have to map from the numeral to the quantity it represents. And again, make a judgment of how they're related. And in this case, identify the numeral that is more. So with that, we proposed a direct semantic knowledge hypothesis where kids' abilities to make these semantic related judgments will be directly related to their performance on a number comparison task. For phonological skill, we proposed a segmentation and maintenance mechanism. For example, with phonological skill, a common task is making rhyme judgments. So for example, here, you'd be presented two images and here two words. So snake and cake. You would have to segment the word to isolate the rhyme component. You would have to then maintain that component over time to ultimately make a rhyme judgment. And a similar process mechanism is involved with the count sequence, where we hear this string and we have to segment it into the individual number words, maintain those number words over time to then be able to reproduce the count sequence. So with that, we proposed an indirect hypothesis where phonological ability will be related to number comparison performance through verbal counting ability. So we had 17 kids participate. It was just a pilot study, and we were also cut short due to the pandemic. We had a verbal counting measure where kids were asked to count to 10 as fast as they could. Then the phonological rhyme judgment task, which you just saw an example of, the semantic meaning judgment task, which again, we just saw an example of, and a number comparison task. And then for our analysis, our primary measure was reaction time. We were specifically interested in looking at the speed of the symbol to meaning mapping, as well as the speed of that segmentation and maintenance of sound mechanism. And we conducted mediation analyses with bootstrap resampling. Because we had a small sample, we decided to bootstrap and resample from our 17 kids. So for results for our direct semantic knowledge hypothesis, the big thing to take away from this slide here is the C prime path, where controlling for count to 10 reaction time, we saw a direct relationship between kids' performance on related trials and their ability to solve small distance number comparisons. And so we resampled that effect, and 0 was not in the confidence interval, which provided further support for this significant direct effect. For our phonological skill, for that indirect hypothesis, however, we did not find any support. So we didn't even see a relationship between rhyme and small distance comparison trials, and then nothing else was significant. And again, we bootstrapped, so we resampled that indirect effect, and 0 was in the confidence interval this time, which was further support that no mediation was occurring. So just to wrap up, we found support for a direct relationship between semantic knowledge and Arabic number comparison performance. So this suggests that the relationship may be the result of this shared underlying symbol mapping mechanism, while we did not find support for the indirect phonological skill hypothesis. And we think it could have been a task design issue where kids were seeing the images and hearing the sound simultaneously. So it could have been that they were just using the images and not actually using that sound segmentation and maintenance mechanism we proposed. So future work could look to just remove the images altogether. As well, we could use a counting task. We just had kids produce the count sequence, where a more appropriate measure could be one that requires manipulation of the count sequence, which is more aligned with what's involved in making number comparisons with numerals. So that is everything. Thank you. And yeah, any questions now, or feel free to reach out to me by email.
Josh will go next. I think you're muted.
All right. Hello, everyone. My name is Josh. I am a PhD student at University of Maryland. I am presenting the results of a project that I did with Richard Crather at the University of Maryland. So executive functions are a set of skills that help individuals complete goal-oriented, effortful tasks. And these skills include working memory, individual control, and cognitive flexibility. And these skills as a whole has been found to relate to math performance and learning and achievement. Today, I focus on individual control, which is the ability to suppress automatic responses. And there has been a trend in examining individual control in math performance for other reasons, but generally its involvement in math learning is not clearly understood. All right. So to address this, I conducted a project in which I partially replicated Gilmore and colleagues' paper from 2015, where they investigated the contribution of numerical and non-numerical individual control to different arithmetic components. We recruited 102 8 to 11-year-olds and 176 adults. They completed non-numerical and numerical individual control tasks. In the former, they had to choose which of two differently sized animals is bigger in real life, and in the numerical task, they had to choose which of two sets of dots is more numerous. And we used the Gabus and Rainbow version for that. And then there were 4 arithmetic tasks that I'm going to mention in the next slide. But I'll note that the innovation tasks and arithmetic tasks were counterbalanced. Also, all of these tasks were done in one session on participants' own computers during the pandemic. So our arithmetic tasks were measured with the same tasks that Gilmore and colleagues had, primarily factual knowledge, procedural knowledge, and conceptual knowledge. I also added a complex arithmetic task, basically measuring their knowledge of order of operations. And what we ultimately wanted to see in our data is how inhibitory control tasks contribute to the variance of each task in both children and adults. First, here are some correlations Here we see the correlations between the tests in both children and adults, adults in the lower triangle, children in upper triangle. We see that both inhibitory control tests significantly correlated in adults, but not children. We also see that in both adults and children, there were significant correlations between factual knowledge and all the other arithmetic tasks, as well as between conceptual knowledge and complex arithmetic. The only significant correlation between inhibitory control and math was between non-numerical inhibitory control, the animals troop, and factual knowledge in adults. Procedural knowledge also significantly correlated with complex arithmetic in children, but not adults. Sorry. All right. So we conducted a constrained multi-group measured variable path analysis. Here, all the numbers are path coefficients, with adults at the top and right at the bottom. So I found only one significant coefficient, that from adults inhibitory control to factual knowledge, which suggests that better inhibitory control is associated with better factual knowledge, or arithmetic fluency. One might conclude that inhibitory control mostly does not contribute to arithmetic skills. However, this doesn't preclude other potential models or analysis. For example, factual, procedural, and conceptual skills might mediate performance on order of operation problems. And I should note that this is not an exact replication, as Gilmore and colleagues used older children and controlled for math achievement. And finally, this was done during COVID, so the variability of the participants' environments could have had an effect on the results. However, these findings are in line with those of Rainbow and colleagues who published this year and found that adults' performance on the animals troop had positive effects on arithmetic fluency, and that Gabus and Rainbow's version of the non-similar comparison task did not at all relate to arithmetic performance. And that is all. Thank you.
Thank you. We have time for maybe one question. Marta.
Hi, thank you, Josh, for this presentation. I'm wondering about the arithmetic fluency task and whether it included a range of operations. Do you think the correlation for the adults relates to their ability to inhibit the solutions to related items? So for example, we know that when people are thinking about addition, they need to suppress the product of the two numbers being added. So do you think that's part of the story for why you see these correlations only in the adults?
Right, no, actually, I only used addition and subtraction for this one. And I'm not aware of addition problems, or at least in addition work where the solutions are being inhibited.
Yeah.
But I know in products they are.
Yeah. Interesting. I mean, it suggests maybe, you know, maybe differences are also being activated and need to be suppressed, but it does seem less likely than products. So, yeah. Interesting.
Thank you. Ray will go next.
Okay, so can people see my slide?
Yes.
Okay. So hello everyone, my name is Raymond. I'm a grad student at the University of Wisconsin-Madison. I will present our work about how teachers in China link representations of mathematical equivalence during their classroom instructions. So equivalence is a foundational concept in mathematics. However, American children often misunderstood equivalence and the equal sign. In contrast, such misconceptions are rare in children in China. So we're interested in knowing why teachers help students build an understanding of the equal sign as representing this equivalency relationship. So in this project, we will focus on the classroom instructions in China. One effective teaching practice is to use and connecting mathematical representations. So for example, the equivalence relationship can be represented with 4 flowers equal to 4 birds. It can also be represented with the symbolic equation 4 to 4. And also, this teaching practice is also recommended by the National Council of Teachers of Mathematics. So in this study, we are interested in knowing what representations teachers use in lessons on equivalence. We also would like to know how frequently teachers link representations during lessons. Third, we would like to know in what modalities do teachers express links? And finally, we would like to know in what sequence do teachers link representations? So we did this work with 3 videotaped first grade lessons on equivalence from China. The 3 lessons all focus on equal, greater than, and less than concept and symbols. And these are the screenshots from these 3 lessons. And more specifically, this is a screenshot from first lesson. This is a screenshot from second lesson. And this is a screenshot from the 3rd lesson. So we coded the 3 videos with several steps. First, we identified the segments of the discourse in which teachers sought to link ideas. We referred to as linking episode. And in each target link, we identified the portion of the discourse that directly expressed the relationship between ideas. We call them target links. And also, we identified the modalities the teacher used to express target links, which include speech, gesture, writing, and drawing. Finally, we examined the sequence of representations used for each concept. So looking at the representation used, we found that teachers use a variety of different representations. Some were more concrete, some were more abstract. And looking at the frequency, teachers produced an average of 13.3 links per lesson. And from the graph shown, it is clear that most links were made in both speech and gesture. Looking at the sequence of the representation used, we found the teachers use 2 types of sequences. The first one and the most popular one is the concreteness fading. So teachers move from more concrete representations to more abstract ones. And the second one is concreteness instantiation. This one is less used, but the teachers sometimes would move from more abstract representations to more concrete ones. This is a more detailed example of concreteness fading sequence. So in linking episode 1, the set of monkeys were linked with the set of rabbits. And then in linking episode 2, these 2 sets were linked with the same quantity. And then moving to linking episode 3, these 2 sets were linked with the quantity 4. And finally, in linking episode 4, this symbolic number 4 were linked together. So in conclusion, we find that teachers use a variety of mathematical representations during their classroom instructions on mathematical equivalence. And our work suggests that analyzing representations and links is a fruitful direction for studying classroom practice. That's both within and cross-culturals. Finally, I would like to thank to the collaborators and the research assistants who worked together on this project, and also NSF for funding this project. That's all for my presentation, and I will end it.
We have time for questions.
I have a quick question.
Okay.
Is there a combination, I guess, of like speech and gesture, or speech alone? Is like one of those found to be most effective?
Since our study is qualitative analysis, we basically analyzed how teachers use what kind of modalities to express the link, and we did not test students' learning outcome, so we cannot see which modality is more effective.
Got it. Okay.
Mm-hmm.
Thanks.
And thank you, everyone. We have 2 more minutes. I'll ask if you have questions for other presenters, which you had not had the chance to ask before. Now it would be a good time for that. Martha.
So I have a question. I just want to thank all the presenters. It was a really great session, lots of interesting ideas. Thank you all. And I have a question for Terry. I was thinking about the diagrams that you use to represent the different operations and the different kinds of start unknown or result unknown kinds of problems. And I wondered how the students reacted to those diagrams, or whether you actually had the sense that students really could grasp the depiction of, say, multiplication versus division when, for example, the numbers didn't match. And didn't ever bother the students that the numbers weren't matching across the text problems and the visual representations?
That's a very interesting question. It seems that the participants are okay with this task, and they didn't ask too much question about like, this is about candy and that one is about water, something like that, and the numbers doesn't match, and it doesn't seem to bother them a lot.
And they didn't. You didn't give a big introduction to explain, what they were representing, or they just.
Yeah, I didn't explain too much because one major thing about these tasks is that I want to look at how they interpret the tasks.
Yeah.
Yeah.
So.
And the significant relation is actually quite strong, and I'm rather surprised.
Yeah. Yeah. Thank you.
Thank you.
Well, thank you, everyone. Thank you to all the presenters. And we had great talks today and great attendance as well. So thank you, everyone, and good night or good morning for you. And see you next week.